All right, can you all hear me okay? Okay, so just to let you know, for my last class, I had internet problem, and I actually had to just record with my video, with my camera at home. So I don't know if I'm going to still have the same problems today for this lecture or not, but we'll see. Okay. All right, so students had questions regarding the exam, and at least at this point right now, I can't discuss the exam because I have a couple of students who have special accommodations that get extra time. So and they're still working on the exam, so I can't really discuss the exam yet. You can come to my office hours tomorrow, and I can answer your questions you may have on the exam. Okay, so I have office hours from 1 to 2 tomorrow, and the link is on Canvas. So you can come tomorrow and I can answer your questions regarding the exam. So the next lab that we're going to work on is called DC circuit analysis. This is a fairly involved lab in terms of the data analysis. In terms of the procedure, to me, it's pretty straightforward. Okay, so you're just going to be measuring voltage and current in this circuit, but you're going to be learning how to wire circuits. So a lot of you folks are still learning how to wire circuits. So that's going to be one skill we're going to hopefully get better at in this lab. I do want to warn you, and this is because of the experience that I've had so far this semester. You need to get started early. I had a couple of students carry out the previous experiment. The day was due, and they had trouble with the equipment. And it was on a Sunday, so it was very difficult for me to help students if they're having equipment trouble on a Sunday, and then the lab is due in the evening. So, that's, and really that's on the student, right? It's on you it's your fault if you wait till the last minute to do the lab. Okay, these labs are designed to be thought-provoking and involves critical thinking, and involves you developing laboratory skills. And they're not the kind of labs that you can just do in a few minutes. Okay, they're designed to make you think. So you want to get started ahead of time. And if anything comes up, then you can ask me questions. And if you have an equipment problem, then we can replace the piece of equipment. But if you wait too long and you have an equipment problem, then you're kind of out of luck. Okay, because we're online, it's much more difficult to do things at the last minute. So you're going to have to show some initiative and start early. Okay. So we're going to be analyzing basically a circuit that we analyze in class. If you look at our videos from chapter 28, I solved, oops, give me 1 second here, this problem. Except that the resistors form a diamond shape. It's the same circuit, except I drew it as a diamond shape. So I went through this problem. In fact, there was 2 versions of this problem I went through. I went through this version, and then I went through one where I actually put a meter across points A and C. So we're going to look at both versions of this problem, and what we're going to be doing is verifying Kirchhoff's laws. And of course, we'll also be using the rules for series and parallel. So everything in chapter 28 except RC circuits is in this lab. So let me draw a picture of the circuit on the board. Let me switch windows. Let me switch views, sorry. And let me draw a picture of the circuit. You have 4 resistors. And please stop me if you're not understanding anything I'm talking about. Okay, so this is the circuit, and R1, R2, R3, and R4 are given to you. So if we go back to the beginning of the document, you're told to make R1 100 ohms, R2 1000 ohms, R3 150 ohms, and R4 560 ohms. And you're going to set up this circuit. So let me show you what I did, maybe to make things a little bit easier for you. In fact, let me change this one more time. Okay, so I built the circuit on a proto board a couple nights ago. And of course, your proto board is squared. So based on your knowledge from how this is wired and your knowledge that you accumulated from the multimeter quiz, you should be able to do this experiment. The only thing is you have to figure out how this works. Although you're going to see my circuit. So, and since it's on video, you can probably play it over and over again. So my circuit that I built looks like this. It's 4 resistors. And notice what I did. I took the adapter piece off our power supply and I taped it onto the circuit so that I can remove the power supply if I need to, just out of convenience. Okay, that's up to you if you want to do that, but this made it easy for me to make the measurements, okay, and deliver power to the circuit. So you'll set this to 6 volts. I have one student who has his own power supply, and they said it's okay. Not too many people have their own power supply, but we'll use this. So you'll wire up the circuit, and you're going to measure the voltage across each resistor. You're also going to measure the current, I sub S, through your circuit. Okay, so you'll measure the current through your circuit. And to measure current, I would probably use this meter just because it gives an extra digit. You want to have at least 3 significant figures in your value for the current. Okay. So I would use that one. And then you can use the little meter to measure the voltages. Now I'll let you decide whether or not you want to leave this in a circuit while you're measuring the voltages. Okay. If you don't leave this in, then you can actually use the same meters. You can use the same meter to measure the voltages. I'll let you decide what works best for you. And then you can think about, what are your sources. You can think about what your sources of error are based on what you did. Okay. Ideally, it would be nice to have 2 meters that are exactly the same, but it's more expensive. The kit would be more expensive. Okay, so you're going to measure this current. I'm going to call this I sub S. And I sub S is going to be equal to I1 plus I2. So when you reach this point, I1 is going to go this way. I2 is going to go that way. And we can measure I1 because you're going to measure the voltage drop. So I1 is going to be delta V1 over R1. I2 is delta V2 over R2. And so I sub S is the sum of these two. Similarly, I sub S is this current plus this current. So what you're going to do is you're going to compare this sum to this measured value. And you're going to also compare this sum to this measured value. And the question is, do the values agree? But in order for you to be able to answer the questions whether or not the values agree, you have to understand the uncertainties, and you have to know the uncertainties in all these measurements. So let me go to your document. Let's go to table 1. Here's table 1. And in table 1, you'll notice that there's a R plus or minus R. There is a V plus or minus delta V, and a I plus or minus delta I. How am I going to get the uncertainty in the resistance? That's true. I can use the last color band, but then I'm going to be using the resistance of the color band. True. What if I measured the resistance with the meter? Let's say I took the multimeter and I measured its resistance. Then what's delta R? Because it's not going to be the color band in that case. Yeah, you look at the last digit, and I got to be careful. You look at the last digit that varies. It's not just the last digit, but you look at the first digit that varies. Here's a problem for you guys in measuring the resistance. Most of you folks do not have alligator clips. So you have these meters with these tips that are not so great. Again, we're trying to minimize cost. So when you use these tips, you're touching the meter, and it's very hard to get constant contact with the resistor using these tips. And so you're going to have probably a greater variation than you would like as compared to, for example, using alligator clips. So your resistance uncertainty might be higher than really what it should be, but that's fine. Don't measure the resistance and then come up with the uncertainty. Okay. All our measurements are going to have the issue because of the fact that we're going to be using this instead of alligator clips. So that's going to affect your measurement for the resistance. To measure the resistance of the resistors, I would put the resistor into this board, but not in a circuit yet, and then so that way the resistor position is fixed. And then I would just take the tips of these guys and try to get as best contact as I could with these tips. Okay. If you have alligator clips, if you are lucky enough to have alligator clips, then go ahead and use them. Okay. And really all it's going to affect is how well you know delta R and how well you know R. Okay. So if you have alligator clips, and some of you folks do, some of you, I know that in the other group, I have a student that has his own power supply, so that's fine. Okay. It's just that, it's going to affect, you're going to get if you're using the clips, you'll get a smaller value for the uncertainty in R. Are we clear on that? Okay. Now, you're going to measure V and determine delta V. And you want to base your uncertainty on the first digit that varies. It's really not the last digit, but the first digit that varies. Okay. If it measures to the thousandths place and the only thing that varies is the value at the thousandths place, then your uncertainty is to the thousandths place. But if your measurement's to the thousandths place and the value varies at the tenths place, then your uncertainty is to the tenth place. Then you probably don't need a voltage reading to the thousandths place, right? Does that make sense? If you're measuring a voltage with the meter to the thousandths place, and you see that it varies at the 10th place, at the, let's say the 100th place, then you really don't need that many decimal places. Does that make sense? Yes, no? That worries me, no response. Okay. So let's say we know delta R and delta V. I want to calculate I, and I want to figure out how well I know I. Of course, we're going to do error propagation. So how well do I know I1? Well, if I know the uncertainty in this and I know the uncertainty in this, going back to physics 205, or your previous course if you didn't take it at Sierra College, then delta I based on error propagation is given by the derivative of delta V1, and this is where the notation becomes a problem, with, the delta I1, the uncertainty in I1, so the uncertainty in I1, the derivative of I1 respect to delta V squared times the uncertainty in delta V squared plus the derivative of I1 with respect to R1 squared delta R1. And of course, the values you put in are your measured, in these equations are the measured values. Okay? I'm looking at your question. For I1, I use this resistance. For I2, I use this resistance. Right? It's the voltage, this voltage divided by that resistance. Right? Is there, do you see, for some reason I'm not seeing an inconsistency. Is that okay, Morgan? I could if I wanted to, but then, because I can write I sub s as the I can write it that way too, right? The current through this resistor and this current through that resistor are the same. They're in series. All right, these resistors are in series. So if I measure this voltage and I divide by the resistance, I know the current. If I measure this voltage and divide by this resistance, I know the current. And these two better be the same. So I can still calculate I sub s from these two, which is I3 plus I4. Which, well, I mean, this is the same thing as I sub 1, and this is the same thing as I sub 2. Does that make sense, Morgan? Or it's because they're in series, I know the current through them is the same. And so we're going to do this twice. We're going to first do it with the top two resistors, and then you're going to do it with the bottom two resistors. So you're actually going to do the calculations twice. Once for the top two, and then once for the bottom two. Okay. And so then delta I1 is calculated by this equation. Delta I2, you change all the ones to twos. And delta I3, you change all the ones to the ones to threes. And delta I4, you change all the ones to fours. I know it does feel weird. And you know what we're doing is because we're actually measuring, because it's based on what I actually measured, right? I'm physically measuring this value. I'm not calculating it. I'm physically measuring the voltage. Right? But that delta V1 and delta V2, I'm physically measuring it. If it was calculated, then my calculation would have everything involved. Okay. I know it is weird. It is weird to see it that way, but it's just the difference between doing a theoretical calculation and a real measurement, because you know the value right away. And it's true that this value does depend on R3 and R4, but you're getting a number based on what the meter tells you. Okay, and that's a good question actually. So if I want to calculate delta I sub S, I get that. Okay, so for table 1, you're going to do this 4 times. And then you're going to, below that, you're going to do this twice. Look, I want you to share your work, but I want you just show me your calculations for one sample. Don't do this every single time, unless you're a glutton for punishment. Okay? But when you show your work, I not only want to see your final equation. If you just show me this is useless. I want you to show me what this comes out to be, and then I want you to show another equation where you substitute the values in. Because a lot of times students make a mistake. They'll either make a mistake in the equation they derive, or they'll make an equation in the values they substitute in. And this is especially true when students, in experiments where students are making a length measurement. So I need to see both. I need to see one sample calculation of your delta I, one sample calculation of delta IS with the equation and the numbers plugged in. So you're doing a lot of error analysis. Now, I was telling the other group, this is repetitive, so one of the things you can do, if you have experience, is to create a spreadsheet with these equations, with the equations, and then you use two cells or 3 cells where you can just change the numbers. Actually, 4 cells. In this case, 4 cells. And you can just change the numbers, and then the answer will change based on the numbers you plug in. Now, I will at the end of the semester show you guys how to use an Excel spreadsheet for doing a lot of calculations, because the last lab you're gonna be getting like 25, 30 data points, and you're gonna be making hundreds of calculations. So you're actually gonna want to use a spreadsheet, and I will do it then. But if you don't have experience with a spreadsheet and you want to set something up in a spreadsheet to do calculations, you can always come see me during office hours or make an appointment with me, and I can do a Zoom thing with you for setting up a spreadsheet. It's up to you. But for sure on the last lab, you're going to have to use a spreadsheet to do the calculations, because if you do the calculations by hand, it's going to be a terrible experiment for you. Okay? Questions so far? Okay. And if you feel I left anything out, you can always ask next week, because I can use next week to answer any questions you may have on this lab. So let me change view again. You do have questions to answer. For example, do your results verify Kirchhoff's current law? Is I sub s equal to I1 plus I2? Taking into account experimental uncertainty. Okay. Do your results verify the voltage law? What does that mean? Well, you're going to pick a loop, any loop you like, whatever loop makes you happy. Okay. Let me find my green marker. And verify the loop rule. So, for example, I can choose this loop and see if the voltage drop across this guy plus the voltage drop across this guy plus the voltage drop across that guy gives you 0. Or you can do it around the 4 resistors. And of course, when you answer that question, you've got to take into account uncertainties. Are there any random sources of errors or any systematic errors that you haven't accounted for? Okay. You pick whatever one makes you happy. There's 3 loops there, right? The sum should be 0 no matter what loop you choose, so you can pick whatever one you want. You can write it in a word. Just say the loop consisting of these 2 resistors and the power supply, or the loop consisting of the 4 resistors. You don't have to draw it. Because the circuit is simple enough, you can just say it in words. As long as what you say conveys the meaning of what you're doing, that's fine. So the second part of the lab, and we analyzed this circuit too in class. And again, if you don't remember, go to the video and watch the solution to this problem. We're going to put an ammeter between points A and C. And you're going to have to keep the ammeter between points A and C during the entire measurement, because by putting the ammeter between points A and C, you've changed the circuit. Ideally, the ammeter has no resistance, and so points A and point C will be at the same potential. And you can measure that if you want to. You can prove that to yourself to show that. Okay? You can prove that to yourself. So points A and C are at the same potential. So really what you have in this case is R1 and R2 are in parallel, R3 and R4 are in parallel, and the 2 combinations are in series with each other. And that's the problem I did in class. Okay? I did this problem in class. So I would go back and look at the video. So in this particular case, well, typically when you do the analysis, you assume it's low compared to R1 and R2. But when you analyze experimental errors, you got to consider that, right? When you consider experimental error, you got to take into account the fact that the meter does have resistance. And in fact, I'm going to have you do part 2 twice. I'm going to have you do part 2 twice. I'm going to have you do it at, hold on a second, 2 different ammeter settings. One ammeter settings, basically the highest current setting you can. If you can do the 10 amp scale, then do the 10 amp scale, but I doubt you can. Then if you can't do the 10 amp scale, then do the 200 milliamp scale. So make the measurement at the highest current setting possible, and then you're going to repeat the measurement at the next highest. The resistance is going to be different. And so how much of an effect does it have on your results? That's the question. Okay. So in my analysis, I'm assuming there's no the ammeter does have no has no resistance, because I'm saying that A and C are at the same potential. That assumes no resistance in the meter. But in reality, there is a resistance. So that's going to cause experimental error. Will I see it? Is that resistance big enough compared to R1, R2, and R3, and R4 where I'm going to see the effect? That's the question. Does that kind of answer your question? Okay. So let's go to table 2. Let me go up on the board. So you're going to have a meter here. This one has to stay here during the entire time. This one, not necessarily. Okay. In fact, for this part, you can't do it because you would need a third end meter. You would need a third meter. You can't have them both in there at the same time. Okay. So I would use the good one, or the more precise one, to make this measurement, and then the other one to make the voltage measurements. Again, make sure all your measurements, if you can, have 3 sig figs in them. Okay. So the current, this current is going to be I3. Let me do it in red, sorry. The current through the meter I'll call I3, which in the lab is called IAC. And this current here will be I1 minus IAC. And you want to see if basically this current minus this current gives you that current. You want to see if this current minus this current gives you that current. You're also going to measure which direction the current, is it going this way or is it going in the other direction? You have to figure that out. I'm not telling you. Which way is the current flowing through the ammeter? And you'll do it twice, and you'll basically what you'll see is that, hopefully you'll see that there's an effect of this guy on your circuit. So in this part, you're going to be measuring V1, V2, V3, V4. You're going to be measuring this and measuring this. But then you're going to be calculating your I's again. But then you're going to be calculating IAC along with the uncertainty, right? I mean, the current through here is going to be this minus that. That makes sense? And then same uncertainty calculations. Questions? No questions? Concerns? Now, one of the things, if you're interested in looking at the resistance of your meter, I show this to the other group. I'll show it to you guys. Let's say I'm measuring current with the big meter. I'm going to set this to measure current. I have it on a 10 amp scale. Okay. What I'm going to do is use the little meter to measure the resistance of the big meter just by setting this up by to measure resistance. I have this set up to measure resistance. Okay, let me change views here. Hold on a second. Okay, so I had this set up to measure resistance. This to measure current. And all I do, if I can do this with both of my hands here, put one into the other and I can measure the resistance. Okay, and you can do that with voltage too. You can measure the resistance of the voltmeter. So if you're measuring voltage with this, set this on the voltmeter scale and see what resistance you get. Okay. And on the 10 amp scale, it's like 0.002 ohms. But if you go on a higher scale, you'll get, like 10 ohms or something. Okay. And in fact, when my eyes are getting bad, I never noticed that this one has a 200 microamp scale. And the resistance on that scale is about 1,000 ohms. It's on the order of 1,000 ohms. So you can see the differences. Okay. So play around with this. Try to measure the resistance of the voltmeter and the ammeter. And get familiar with these things. There's instruction manual. There's a instruction manual that comes with these meters. Read them. Okay, read them. Questions? Okay. And if you have questions or if you feel I left something out, just bring your questions next week. Start on this early. Now that you've had the exam, you should be able to do this measurement right away. Okay, and then you can ask me your questions next week. Don't wait till the last minute, please. And I know a lot of you folks have experience with doing this, but after it's been a while since you've done this because it'll be the first time this semester we're doing air analysis. Get started early so I can answer your questions. All right, so there's a bunch of questions and calculations you have to do. Make sure that your calculations and any equations you write are typed, okay? Using the equation editor in Word or math type or whatever equation editor you want to use, but it's got to be typed. Do not handwrite equations. Do not handwrite calculations. Okay? Same as last, if you took 205 with Shakel, I have the same expectations. How do I find the uncertainty with the resistance again? So you measure the resistance and look at the meter. Find the first decimal place which it varies. So for example, I'm just going to make up a number. Let's say, well, let me do this. So you want to know how I determine delta R. Let's say you see this number vary. Okay? Let's say that number varies. Then I would say, of course, now this is going to be an estimate. I would do this. And you can see how much this varies. You might say it's 2. I don't know. Okay. Everyone's going to get a different value for this. Okay, everyone's going to get a different value for this. It's not going to be exact. This uncertainty. Yeah, it can be 0.01, it can be 0.03. Yeah, yeah, okay. The second statement you said, Morgan's better. I know it's weird, but otherwise I'd have to make you do a bunch of measurements and calculate the uncertainty. But even then, if you do that, I mean, if the number, like the value I have shown there, if it varies to the 10th place, how do I know what number I should write down? Because remember, your hands are not perfectly still. The contact you're making between the tips of the meter and the resistor isn't really very consistent. So how would you pick between two values? If you look at this, I mean, if you think about how these, you just stare at it for like 10 seconds. And if the value goes, and I don't care about this number. If the value oscillates between those two values, just take the average of those two values and say it's 3.45 plus or minus 0.03. Does that make sense? Just look at how the value, if your measurement oscillates between these two values, then pick a number in between, and the uncertainty is going to be half the difference. That's all we can do. Sometimes as a scientist, you don't have the right answer, and you got to do the best you can. Right? And so you try to use the best methodology given what you got. And that's what you would do. Because we're not always going to have the answers. Ideally, if you had alligator clips and you had good contact, some of you folks might have alligator clips, but if you don't have good contact, if you have alligator, you have good contact, then what you can do is you can see how much that last digit varies. Or you can go by the precision of the meter as stated in the manual. Okay, you go by the last digit. If you have good contact, you just go by the last digit. But if you don't, and you get values that are going to oscillate, you'll see your values oscillate. You'll have to do that. You're going to have to estimate that. Okay. It's one of those issues, places where you're dealing with a gray area. Yeah, so that one's a tough one, isn't it? Wouldn't the uncertainty be point? I would still say 0.1. I'm sorry, 0.01. All right? Actually, I think you meant 0.005, but yeah, I would just say point. I wouldn't write the uncertainty smaller than the digit it varies. Okay. Yeah, and if we had a better methodology to make the measurements, then we would have a better way to determine the uncertainty. We'd say, oh, well, it's the precision of the meter. Like if you use a balance, an electronic balance, you put the mass on the balance, and the value will vary on the last decimal place. That's because of the precision of the meter. This is different, though, because your contact is not going to be consistent. So we got to live with that, unfortunately. Yes, we'd have 0.01, 0.01 instead of 0.005 because you know that the number varies to the 100th place. And again, that's one of those gray areas too, okay? Okay, so you have actually 6 questions in part 2 to answer. And then the last one, you want to derive an expression for the current through R1 when the assume ideal ammeter is connected between points A and C. So this is where you're doing some theory, okay? And when you do a derivation, make sure that you kind of say what you're doing in the derivation. Just imagine your textbook. Imagine having a textbook with a bunch of derivations, but no explanations in derivation. My question to you would be, can you learn from that? And I hope you say no. Okay. So when you do a derivation, like in number 6, oops, sorry, I'm not showing you the document. When you do a derivation like in number 6 here, you kind of want to say what you're doing. You don't have to write paragraphs. You just want to write short sentences. I do this, then I do that, then I do that. Something like that. Something brief to let the reader know what you're doing. Right? You're not writing a book, but you're trying to let someone at your level understand what you're doing. Are we okay with that? Okay. I want to mention one more thing. It's something we're really not considering in this lab, but if we were doing this lab in class, I would have you consider it. And it's the following. If you look at the resistors, they come in different sizes. I mean, physical sizes. You'll have a resistor with a color code, maybe it's like this. And you might have a much bigger one, like this. And the physical size of the two is important because they reflect the power rating of the resistor. So different size resistor reflect different power ratings. So the real small resistors are about 1/8 of a watt. That's an 1/8. Then there's 1/4 of a watt, 1/2 a watt, 1 watt, and then they get bigger and bigger. Okay, so what does this mean? What does the power rating mean? It means that that's the most energy you can put into it at any time. If you go above that value, you will find that the resistor will start to heat up. If the resistor heats up because it can't dissipate the energy fast enough, its resistance will change. And if you go too much above, it'll start smoking and it'll turn black because you're going to burn the resistor. So they all have a maximum power rating. And that will allow you to find the maximum voltage you can place across the resistor. Or you can figure out the maximum current you can place through the resistor. Okay? If you're designing a circuit, you want to make sure that your power supply is not too big to burn your resistors. Of course, you need to find a weak link in your circuit. Normally, in a lab like this, what we do is say, what I would have done is say, figure out what is the maximum voltage you can apply to your circuit and do it. Set your power supply voltage to the maximum voltage you can apply to the circuit, assuming these are 1/4 watt resistors. That's if we were in class, if we were in Sewell Hall doing this experiment, this is what I would have you do. Because that's an important design consideration anytime you're building a circuit. What is the maximum power rating of the resistors, and what is the maximum voltage I can apply to my circuit? Okay, that's an important consideration. That would be a good exam problem, wouldn't it? I could have asked that on my exam, right? On today's exam. What is the maximum voltage I can apply so that I don't burn out any resistors? You actually had a question similar to this in the capacitor homework. There was a capacitor bank, and you were asked, what is the maximum voltage I can apply to my circuit so the capacitor doesn't go bad? Okay, that's a design consideration. That's an engineering consideration to think about when you're designing a circuit. And so it's important to consider also the power rating of these resistors. And even though I'm not having you do that in this lab because we're at home, you know, we're doing this at home. We don't have the same equipment. You don't have the same equipment at home as we do in the lab. So if you blow something, you're in trouble at home, but not in the lab. We can replace things. Okay. So even though we can't do this, you should be aware of this. That's why I mentioned this to you. Okay. Questions or concerns? All right. So I expect you next week to come to me with questions about this experiment. Okay, I expect you to ask me questions about this experiment, the error analysis, anything. So I want to have a discussion. So I want you to come prepared next week to ask me questions. And if not, then if I'm behind in class, then I'm going to use the time to catch up in lecture. Okay? Are we okay? Okay. You guys still there? All right. It's a small group. All right. So I'm going to stop here then. And I'm not going to hold the recitation because we just started chapter 29. And you know, not everybody has, very few people started the homework. In fact, I got to change some of the homework problems because of, I changed the addition of WebAssign. Okay, so we'll stop here. Have a good weekend. Unless I see you tomorrow in office hours.